Welcome, everyone. So I knew I would have been the last talk of the day. So I decided to kind of start with these two numbers, hoping that I'll get your attention early. So we see 1.9 million and 2 hours. Sounds like a good gig, right? It was actually an attack that happened a few years ago. And in this talk, I want to explain you what happened, which is that an attacker stole $2 million within 2 hours from users of a crypto exchange. So I want to explain in this talk what actually happened, who is to blame, and what else is possible. The formal name of my talk is The Network Beneath the Computer in the Sky, which is the theme of the summer school. And I'm Apostolaki, I'm from Princeton. So let's go through the incident, shall we? We have 4 entities. Let's get to know them. We have ClaySwap, is a DeFi exchange of the Clayton blockchain. Decentralized token swap platform. Users connect through it to their wallets. They have a regular web front end to trade cryptocurrencies. Really nice entity. Then we have Kakao Corp, which is a Korean tech giant. Think of it as Google, but for Korea. Not a blockchain entity, but a web infrastructure on which ClaySwap depends on. Then we have ZeroSSL. ZeroSSL is a certificate authority among few hundreds that we have, or 150. And its job, it's perfectly legitimate, is to issue TLS certificates that browsers trust. It uses domain control validation, which I will explain what it is, to verify that the requester controls the domain that they're asking a certificate for. And finally, we have the attacker that managed to steal this 2 million in 2 hours. Before we go to the attacker, in order to understand the attack, we need to understand what happens during normal operations. So during normal operations, I'll have my user. My user will visit the ClaySwap interface, front end, which will cause them to load JavaScript from ClaySwap, our CDN. They will visit ClaySwap, and that will cause them to load a JSON file from this CDN. What's important, and what's the main part of that I want you to remember from this talk, is that all this happened over the internet. So I have my nice user browser. They try to go to ClaySwap, and because of this, they will actually end up loading a JavaScript file from this web server. This will happen over HTTPS, which is a protocol that is secure. Make sure that the entities are authenticated. In other words, I have a way for the user browser to check that the web server they're actually talking to and receiving files from is indeed who they claim to be, which is developerskakao.com. And during regular operations, they will send this nice JavaScript, and everything is great. What's really important here is I told you that the browser has a way to know that they're indeed talking to kakao.com. And that's what we call a certificate. It's a signed document that proves that they're indeed this server. Who issued that? The ZeroSSL, which is, again, a benign entity. What happened during the attack? Well, during the attack, the attacker somehow managed to convince the browser to connect to them, and they actually delivered a malicious JavaScript that pushed all the tokens that they were transacting to themselves. So regular operation, user to ClaySwap to Kakao, which is a CDN. During the attack, user to ClaySwap to the attacker, rather than the Kakao CDN. And now I have a really interesting question for you. Who is to blame? The user? Maybe the user's browser? Clay swap? Our CDN? The weather? My mother? What do you think? Who thinks the user or their browser? Who thinks clay swap? Who thinks the CDN? Okay, we have at least one vote. I appreciate that. My mother? I've never have, oh my God. She's to blame for so many things. I don't want to push this as well. But, okay, do you have other ideas? Do you want to tell me?
DNS.
Who? DNS? DNS. Okay. Interesting, yes. DNS could have been to blame. The certificate authority. I did not even include this. Yes, that's great. Yes. Zero SSL could be. Yes.
Shouldn't there be a browser extension that the user is supposed to check before approving the transaction? So shouldn't be the browser extension that handles the wallet?
Mm-hmm. So maybe it could have been the browser did something wrong. Maybe the zero SSL should not have been issued a certificate. Maybe DNS replied with the wrong IP address. Let's see what happened. What I want to emphasize here, and that does answer the DNS question, is that actually there was a certificate that was issued and delivered to the browser. So the browser couldn't have done anything. But we'll talk about it more. So fundamentally, to understand who is to blame, we need to understand why did the browser ever talk to the attacker? They were talking to Kakao. Why did they start talking to the attacker? That's one. The second thing is, how did the attacker manage to go past TLS? How did they prove to the browser that they were Kakao, since they were not? And we will see this. To understand this, we have to cover some background on internet routing and the certificate ecosystem. All right, so let's start with, why did the browser ever talk to the attacker? To understand this, we need to understand how the internet works. So again, during normal operation, the user talks directly to the web server. But how does this happen? Actually, the web server in the CDN has an IP. The internet itself is not a monolithic thing. The internet is a network of networks. And that's exactly what Tim said in the beginning that we often forget. The internet is a network of networks. Each network is an independent entity, which we call autonomous system or internet service providers or ASs. Think of autonomous system as Swisscom, AT&T, Comcast. But there are actually 70,000 of those entities that independently manage their network. Now, focusing on the web server of Kakao.com, which is sounds like it's the root of the attack. They're hosted somewhere in the internet, and how do we know where they are? They actually have an IP address. Their provider, say AS8 in our example, is responsible for creating what we call a BGP advertisement that covers the IP of this web server. BGP is the default internet routing protocol. Is that what allows us to find our path through this network of networks to the destination that we want to go. So this BGP advertisement is propagated AS by AS among all the routers or the network devices in the internet until all ASs, all hosts, know how to reach the web server of Kakao.com. For example, our user browser will use this path by default. Now, the problem with BGP, which is the default internet routing protocol, we don't get to choose or change it, doesn't check the legitimacy of advertisements. So an attacker is free to actually advertise any prefix. In this case, our attacker advertises an IP that covers the IP of the web server that we're interested in, and observe that it is a more specific one. It is a /24 compared to the /23 of the benign advertisement. Both advertisements will be propagated in the internet, but routers actually pick the most specific one by default, the longest one. So the effect of that is that the whole internet will actually believe that to reach the prefix of the web server, they will have to go through the attacker. And this is exactly how our browser ended up talking to the attacker rather than talking to the web server. But still, this doesn't answer the question of why did the browser believe that they were actually talking to Kakao.com? And just to go back to the DNS, maybe is to blame, the same as what the attacker has achieved so far could have been achieved with DNS. So one could have attacked DNS itself so that the user browser, when trying to resolve the domain name, so developers.kakao.com, they could have found a different IP from the real IP and hence be gone to another place. So these are equivalent at this point. I could have attacked DNS or I could have attacked BGP. And the effect of this is that the browser will try to load the JavaScript from the attacker. But here's the main problem. Now, the attacker has to prove to the browser somehow that they are actually Kakao.com. To understand how this was possible, we'll have to understand the certificate ecosystem. So to understand the certificate ecosystem, we just need to understand this triangle. The user browser comes pre-configured with some certificate authorities, about 150, that they trust. And the certificate authorities themselves trust different web servers. When we say trust, we mean that they have a way to verify that the particular domain names correspond to them. They own these domain names. And because user browsers trust the certificate authorities, and the certificate authorities trust the web servers, they issue certificates for them, hence the users can actually now trust web servers. But the key question here, and the key vulnerability, this is why the PKI ecosystem, public key infrastructure, is vulnerable, and hence HTTPS is vulnerable, is how does the certificate authorities actually know? How can they prove that developers Kakao.com are indeed the owner of this domain name? So let's see how this is done. Developers Kakao.com will actually ask a certificate authority like Open or ZeroSSL for a certificate that they own this domain name. For the certificate authority to be able to prove, to verify that whoever is asking for this certificate actually has access to this domain, not access, they own the domain, what they do is that they will ask them to load a particular file in a path on this domain. The certificate authority will then use HTTP, no encryption, no authentication, to pull this file from this domain name. So if they own the domain, they will be able to do it. If this is verified, then the certificate authority will actually issue a certificate which the domain can actually give to whoever is trying to access it to prove that I have already talked to the certificate authority, and the certificate authority thinks that I own this domain. Are we good with this? Questions? By the way, questions is your way to prove to me that you're alive or you're listening a little bit. So it's a great thing.
You mentioned before the IP space with I think 83 and 82, and I don't understand why it can be anything but DNS, because if I send like the URL, and there's a DNS that translated into IP, so it can be anything else but an issue with the DNS.
Awesome. Okay, so DNS responsibility is to go from domain name to IP address. Why is this useful? Because we cannot remember numbers. Okay. Once I arrive at this number, at this 32 or 64 bit number, imagine, let's say, when we're sending letters, we don't send the letter directly to the exact address of a building. We first go to the country, to the continent, the country, the city, the town, and then we go. This is exactly how the internet also works. We don't route by IP, we route by ranges of IPs, by prefixes. So yes, DNS is responsible for mapping domain name to IP, but BGP is responsible for telling me how to go towards this prefix that contains this IP address that I have resolved the domain to. Does this make sense?
Isn't that vice versa? First of all, you fetch the IP and then...
I type my website, load DNS, DNS gives me the IP, and in order for me to connect to this IP, I ask the first router on the path, okay, how can I go there? And the router has received all these BGP advertisements and just knows the next hop. It doesn't even know the full path. Yes?
Okay, I'm just curious to know how they manage to hold. So the attackers need to know how the zero SSL verify. So what's the content of the file and location of the file, right? I know they can have tried to register themselves to know, but yeah. I assume there is some randomness there. You need to put something that's unique.
Agreed. Yes.
So probably zero SSL is too big, because then NAS is insecure by definition. So it takes the first response that receives.
Correct. So I need to make sure that I'm the first to be asked. Correct? Yes. Okay. We'll see how they did that. All right. So we're good up to here. All right. Let's go answer this question. This is the only place where I don't have encryption yet, right? This is regular HTTP. Whoever asks first can actually deliver. Recall that the attacker has actually performed a BGP hijack. So what the attacker does is that they ask for a certificate for the particular domain. The certificate authority will issue a DNS query, will find the correct IP, but then when they will try to go to this IP, they will actually go to the attacker, who, because they issued themselves their request, would be able to just serve whatever file they have been asked to do. So just by doing this, they were able to acquire a certificate and actually show the certificate around, such that your browser is actually super happy, and they should be, because they see a certificate from a certificate authority that they do trust. Yes?
So the attacker had a full certificate for Kakao.com.
Yes.
But how did they manage to only steal 2 million in 2 hours? Because, I mean, sure, it's a high number, but Kakao is gigantic. I mean, I'm sure they could have stolen way more.
I think, although I would be fine with 2 million, but jokes aside, they had to, so I think they were constrained by who actually went to their wallet at the time. So because it relates to, I'm trying to make a transaction, so I'm going to the website, I'm giving you some of my credentials because I trust you, you look totally legitimate. And once you have this, you can go and perturb my transaction to whatever you want. But I had to first contact you.
Right. So you say this thing worked, but it's quite short-lived as soon as you perform the attack, so everybody realizes that everything realigns quite quickly. Is that
Actually, all right, it depends on what you mean by quickly.
right?
So the problem with BGP hijacks is that they're resolved at human scale. People call each other and ask them to filter certain prefixes, advertisements. And even Google, like somebody hijacking Google's prefix, needs 2 to 3 hours in recent attacks. So that's the problem. Now, that's the problem. Actually, in this case, the attack was not resolved. The attacker just stopped. During the attack, people did not know exactly what was going on, and their best guess was actually DNS. So they were trying to see whose DNS is being spoofed. Yes. So in this case, the attacker actually just stopped. We're kind of good. And the cool thing is that there had been similar attacks during, not against crypto, but during the same period. More questions? Are we good?
Yeah. Isn't this kind of why you have security transparency, or use blockchain in general to slow this down?
So let's first, just to make everyone, make sure that everyone is on the same page here. We have the certificate transparency log. Why do we have this? This is an append-only log that everyone that issues a certificate should also write it there. Why is this? Because if I have a domain name and somebody has just received a certificate, I want to know. So it's basically to protect me from somebody else that managed to issue a certificate from my domain name. Now, the issue here is that in this case, the same certificate authority that has signed the true certificate also signed the new one. This is a perfectly, it looks like a benign operation. Certificates need to be reissued frequently, so it wouldn't even look that weird.
Well, you could want to look for like a week. Like you could wait for a week for, okay, is it a reissue, or this is was the attack a reissue? On the reissue of this.
Okay, so anything we do in the internet, even the most secure things, are often a battle between usability and security. You're right that a lot of the attacks could have been prevented if I just waited. The same holds for BGP. If I see there is a new one advertising a prefix, I could just wait and never contacted who I want for a few hours. That's that. It's not.
I guess my point is that like in a reissue, I have the old certificate, right? And then,
yes.
Let's say today they issue the new one.
Yes.
I can still use the old one. Like it's not that the key is lost, right?
Wait. So who offers the certificate? The web server. So I'm contacting a web server, and they return with a certificate that is valid.
Right. You wait a week. So like the old one is still working. It's not. If they lost the old one, that's it. Like if the exchange lost their certificates, I would be worried anyways. So like the theory is if they want to replace it, fine, they'll publish it, and after a week I'll use it.
They will publish it and never. So the thing is that when I do a request, they send me back their certificate at the time. I don't keep everyone's certificate and check whether. So I basically check whether what they offer is signed by a certificate authority that I trust. Right, I don't have everyone's certificate and check whether they sent me the correct one.
Right? So I see that it's like it just happened the last hour.
Yes.
So I should not accept it. Right?
There is a whole other problem with certificate revocation. So sometimes another way that you can attack this infrastructure is, in fact, you steal their private key, and then I have the need to very fast revoke a certificate. So that will create another issue.
That's fine. No, but I'm saying if the exchange needs to very fastly revoke the certificate, then I might not want to contacted that admin. Like now I know that this exchange is like offline, like there's a problem. Somebody stole the certificate. So it actually makes sense to wait. A week is an exaggeration. I'm just saying, anyway, this is just about
Yeah. I totally understand I think I understand what you're saying, but it always, you have usability and you have security, and you need to decide where you want to lie. What's interesting though is that the previous similar attack that had happened, actually the attacker hijacked, and then the users saw this thing that says, oh, this domain is actually really sketchy. It used to be HTTPS and now it's HTTP. Do you want to continue? And they would click yes. So that was my Ether wallet. So I agree, but we have some space to cover. It was a really interesting attack in that it actually issued the certificate itself. But you're totally right that we can make the certificate issuance faster. Another problem with this is that the certificate authorities, they are really, for example, it's Encrypt that is trying to have multiple vantage points such that they don't have the problem with PGP hijacks. They're completely, they don't have a great financial model. That means that they're not for profit, right? So it actually becomes really hard for them to operate just for having the first extra security measure. So it's not that easy, but it's not a technical problem. This is what I'm trying to say. It's more of this is how we have been doing things. Yes?
Yeah, just what you mentioned is correct, that you need a person to fix intervention, human intervention to fix the IGP when you broke it. But my opinion is that if a person was working 0 SSL, this will not happen. Because you don't accept just a request from someone. No. So is the trade-off here is 0 SSL, these other ones, they provide free certificates, but they don't really check the authenticity, right?
Yeah, so how does the certificate authority actually verify one's identity? There are some that do different types of checks, but so for example, some will check whether you have a mail from the organization. I mean, there are different ways, there is not a perfect way, and given the fact that I want to issue certificates reasonably fast, because I want actually everyone to use HTTPS, there's a trade-off there. All right, it's great that I have questions. That means that you're following. All right, so just to summarize, I did a BGP hijack. I'm the attacker. I did a BGP hijack. I got a certificate, and that allowed, and then because I was already doing a BGP hijack, I was able to attract the traffic and deliver my malicious JavaScript and then steal the funds. What I want to emphasize here is there is no blockchain vulnerability, no smart contract smartness, no consensus failure, no 51% attack. It was purely the internet infrastructure is not great. And this is something we have to keep in mind. No matter how much you secure your overlay, you always have to look at the bottom. And the attacker will attack, of course, the weakest link. So this is exactly why this matters. It was the first known BGP and TLS attack. To be fair, there was a paper at Usenix from Princeton researchers that described the attack before it happened. It's not unique to ClaySwap, of course. Any web server would have this issue. Any DeFi application that uses some web frontend would need to use TLS. And it really reveals this trustless paradox. What do I mean by that? We have the users that are decentralized. We have the blockchain that can be decentralized. And we can trust both. But in the middle, everything is actually centralized, trust-based, and really vulnerable. This is a call to work in networking, almost like an advertisement. But think about it. Our browser trusts 150 certificate authorities. Each of these certificate authorities can actually issue a certificate for whatever website. DNS, centralized as well. I call, okay, whose domain name is that? I get an IP. Not that easy to check whether that's true. BGP, no authentication. I say this is my prefix, I own this, I propagate, I'm cool. Web frontend can be hosted in whatever CDN, there is a dependency there. RPC provider, so many different vulnerabilities can actually cause a dependency that would then expose a vulnerability at a higher layer. Yes?
Can I ask, did the website have two-factor authentication? Because it seems too easy to just access the account of someone, right? You need cookies, you need...
You're right. I guess they did not have two-factor authentication, or they would not request this every time I log in. While I was in Switzerland, for example, every time I wanted to go to my bank, I had to solve this weird problem. Like, it was really hard. Then I learned, I think it was Chapkun's, like a professor at ETH, and he was really proud. And I was like, but you know what? I feel stupid every time I log in. It's, again, an issue between how do we make secure solution also usable. So now that you know more.
Just make sure I understand. So
Yes.
ultimately what they attempted, so there was code whose job was to prepare the transaction and sign it, and that code got swapped out.
Yes. Yes.
They changed just the destination or also the amount, or
I think it was only the destination.
so there was $2 million worth of legitimate payments that all got the destination.
Yes. Yes. All right. Okay, so who is to blame now? What do you think? The users. Clay swap. The CDN. The certificate authority. The certificate authority, okay? What could they do? They rely on BGP, right? So that's another problem. It's really hard for us to blame anyone other than the attacker. Everyone points their finger to somewhere else. Yes?
So I think it's quite related, right? But in the threat model for the clients, let's say, on most blockchains, it's a bit of a fiction. But it does rely on that weird thing where you have the browser and then you have a totally separate trusted entity, which is usually an extension. And we really assume that the user, once it inputs all the things that it needs in the browser, manually looks at that transaction that is generated by the extension, remembers by heart the destinations and the amounts and the smart contract address, everything else, and only clicks on sign for the extension after verifying all of that. I agree no user does it. But if the user was doing that, what could have gone wrong?
Where does the user look at?
Only the extension, not even the browser.
But who decides what is being written in the extension?
Well, that's the thing. You're supposed to get it once and verifying its hash on the chain.
Also, I have to look at the chain at the same
It's a
time.
fiction, but it is how who tells users to do it, right?
Good for, yeah, I totally agree with you. I'm not saying this is an attack that we don't have the technology to avoid, but the infrastructure that we have in place is not that. And I feel it's completely unfair to say, but I have this solution. Like, if you compare the hashes in the chain, you stay in one leg, you yell, you look at the moon, then it's secure. But are we doing our jobs right?
I completely agree. But this is why this attack, I would say, is technically outside of the threat model.
Yes. And this is why I'm in academia and I'm not owning a company. You're right. I totally agree with this. Okay, cool. We need abstractions, otherwise science cannot grow. That said, I also think it's really important to keep the full ecosystem in mind and try to reduce the assumptions that we're making. All right. Okay, what else is possible? sky is the limit, but I will tell you a few more attacks. But first, I will tell you how to look for them. And that's, keep in mind, always, the different layers. Usually, when people talk about blockchain, they focus only on the application layer, which is nicer, and we keep security in mind. There is cryptography. Smart people work here. And then we have networking people, us, plumbers, right? We work at this part. And this is a mess. The problem, though, is that the application layer depends on the peer-to-peer layer, which is responsible for actually running the blockchain, which actually depends on the internet layer, which is responsible for making sure that the nodes that run the blockchain actually can communicate. So if you're trying to find attacks, follow the dependencies. Let's zoom into this a little bit more. The peer-to-peer layer is responsible for these three operations. Peer discovery, so how do I know which other node is running this blockchain that I'm trying to run? Transaction propagation, the peer-to-peer layer is responsible for propagating the transactions such that everyone can verify them, everyone can have the same view of what everyone is trying to do on the network. And block propagation, everyone needs to have the same view of the chain. So block propagation is really important, and it happens over the peer-to-peer layer. If an attacker is able to compromise either the peer-to-peer layer or the internet layer with BGP, with DNS, with TLS, whatever, they can actually compromise the blockchain without using any fancy or breaking any cryptographic primitive. This is what I really want you to keep in mind. So there is a ton of different attacks in the peer-to-peer and network layers. And I have some families here, and there are different ways to actually execute them by exploiting some part of the peer-to-peer layer or some vulnerability in the internet. And more importantly, you can combine them. So I can have different ways to attack identity. For example, I can issue multiple different nodes. I can have arbitrary many nodes. They're really cheap. And I can connect them to the network and affect how I can do other things afterwards, but that's my first step. Or I can have them join and leave the network, and because of this, affect how the graph, how the peer-to-peer network is actually connected. What else can I do? I can have topology attack, like Eclipse attacks, in which the attacker uses the fact that they can issue different identities, more identities, and connect the malicious entities to the victim nodes. This is what we call an Eclipse attack. I'm preventing them and I can even create a partition attack. I will give you particular examples of some versions of these attacks, but fundamentally, what I'm trying here is to attack the peer-to-peer layer, the topology itself, either by connecting my malicious nodes to some part of the network or by partitioning the network, hence preventing it from exchanging information, preventing nodes from exchanging information. I have a ton of propagation attacks. I can start delaying transactions. I can prevent transactions from being propagated if I control either the peer-to-peer layer or the internet itself. By control, I don't mean control the full, but being able to compromise it. I can also have different types of information attack. I can look at the propagation of transactions and de-anonymize users or nodes. I can map the exact peer-to-peer topology and use this to attack more precisely. I can do different types of fingerprinting. What I'm trying to do here is that I'm trying to tell you that there are multiple families of attacks that can be combined, and each family of attack can be implemented with a different way by exploiting a different subset of everything related to peer-to-peer or to the internet infrastructure. And this is why it's really important to understand cross-layer dependencies. Now I will walk you through a few examples. So far I have been telling you peer-to-peer network. I'm not sure whether that's very clear to everyone, but the idea is, say for Bitcoin, I have multiple Bitcoin nodes. They're scattered around the globe and they establish random connections. And their goal is to keep a record of all transactions ever done with Bitcoin. In this slide, you see different transactions, and they're grouped in blocks. And then the blockchain is just a chain of these blocks. And its block points to the previously created one. And of course, this forms a ledger. Miners are responsible for creating new blocks, hence extending the ledger. So these are things I hope you already know or you have heard by speakers before me. The interesting part for me starts here, where you have this peer-to-peer network, and the goal of the nodes is to actually propagate the transactions. For example, here is a new block. It has been mined. In Bitcoin, a block is being mined every 10 minutes, and the nodes propagate this information to all other nodes. But again, this happens over the internet, which, as we learned, is a network of networks. And that creates a lot of problems. I'll give you a few attack examples that work on Bitcoin and, in fact, in other cryptocurrencies or blockchains. The first attack that I will describe is what we call the partition attack. So the goal of the partition attack is to split the Bitcoin or any other blockchain network into two disjoint components such that no information can be exchanged between them. The impact of such an attack is really worrying. It can be a denial of service attack, as Bitcoin clients and wallets cannot securely propagate transactions. It can cause revenue loss, as blocks mined within one of the two components will be eventually discarded, together with the miner's rewards. And of course, during partition, I can have double spending, because I can spend the same Bitcoins in each side of the partition. So let's see how it works, now that we know how BGP hijacking works. So let's say that the attacker in the middle wants to isolate the Bitcoin clients that are in the shaded gray region. What the attacker will do is that they will create a BGP advertisement pertaining to all prefixes of nodes in the gray zone, and they will cut the connection crossing the partition, so connecting the gray zone with the rest of the network. Now, once a block is being mined, it will only be propagated within the gray zone. Reasonable? Not all partitions are feasible, but there are ways you can go around this. Another attack you can also pull off is what we call a delay attack. And there are different ways of doing this. One particular one, and what is the effect first of a delay attack? The goal of the attacker is to delay the propagation of blocks. And this depends on who is being attacked. If I'm delaying the propagation of a block to a merchant, they can accept Bitcoins that are already spent. If I'm doing it against the mining pool, they will waste their mining power working on a block that will be eventually discarded. If it's a regular node, I'm actually preventing them for contributing to the peer-to-peer network and hence to the security of the blockchain itself. The way it's being done, this time I don't need the BGP hijack, but because the internet, as we said, is composed of networks, and it's a network of networks, and I don't control which network see my traffic, what can happen is that an attacker can be between a benign node or all benign nodes that the victim is connected to. By manipulating these messages, they can achieve a really they can prevent them from seeing new blocks for a good amount, 20 minutes in this case. I'm not going through the very specifics of the attack, because a big part of it is that it depends on the fact that Bitcoin is unencrypted, which is something you should have fixed, but that's another discussion. Fundamentally though, if the attacker is on path in a communication, they can prevent this communication from happening. Depending on how much they know for this communication, that can be more or less stealth. But they can totally, by controlling the network, actually prevent the propagation of certain blocks.
So you're talking about
Yes.
So when you're talking about it being unencrypted, you're talking about actually the peer-to-peer messages.
Correct. So one would assume that they don't need to be encrypted because they have nothing really to hide, right? And just the propagation of something that is already known. But the problem is, by them not being encrypted or authenticated, I can essentially change part of the message that corresponds to what they're asking for. Now, if you combine this with the fact that the peer-to-peer network is trying to be as cheap as possible, because there is a ton of messages that are being propagated. So for me to be a good node, if I have requested some information from my peer, I will wait for them to deliver it. I will not start broadcasting, oh, I need this. So because of this need that I have, and because the peer-to-peer network needs to be somewhat reasonable in how much information is being exchanged, you end up with this type of vulnerabilities. Another attack that is possible is what we call the perimeter attack, and it's one in which the attacker is able to connect the pseudonym of a user to the transactions that they are, hence the transactions that they're creating, to their true identity. So Bitcoin is pseudonymous. That means that when a physical person, say Alice, buys something, they use their pseudonym. But the problem is that they can issue transactions in multiple different places. Hence, it's easy and it's problematic if I'm able to connect the pseudonym to their IP, because they use the IP to connect to different other platforms. Hence, it's easy for me. Once I have the connection between the pseudonym and the IP of a person, it's trivial to me to know who this person is. So the goal of this attack is to connect the pseudonym with the IP address, the address of this person in the internet. And the way we do this is by observing how transactions are being propagated through the network. Other versions of this attack is where I will have multiple connections to the victim node, and I will try to infer whether they have started propagating a transaction by doing this. But this is, of course, limited to how many different connections I can keep with a particular victim. Now, the problem here is that the underlying network you never see. As a node, you see who you're connected to, so you can try to have some diversity. I don't want to connect only to nodes that are in a particular country, or only to nodes in a particular prefix, or I don't want to change all my connections really fast. But what we infrequently think about is that regardless of who I'm actually connected to, my traffic is being routed through internet service providers, ASs, that I don't pick. And these ASs actually passively observe the traffic that I'm being sent, and hence they are able to infer what I'm doing. In the particular attack, what we managed to do is to connect a user with their pseudonym. Similar attacks are possible in the internet to infer, say, which website you're visiting, regardless of whether you're using encryption, of course, or not, or what applications you're using, or what type of device you have. So it's just an extension of vulnerabilities that are known and well studied in the internet, hence less thought about when we're talking about blockchain. We often think, okay, who am I connected to, rather than who am I connected via at the internet layer. Okay? Yes?
So aside the last attack that is against privacy, let's say, the two first, is it okay to say that it would only apply to systems that are synchronous, not to the family of protocols that are partially synchronous or asynchronous? or completely asynchronous?
Can you give me an example?
Well, Bitcoin would be an example of the synchronous one. Hotstaff, all those that have been presented this morning, like the simplex variant, would be partially synchronous.
So, I totally agree with you that depending on the specifics of the protocol, the effects of such an attack differ. But what's important to remember is that at the minimum, it would be a denial of service, which is already bad. I totally agree, though, that essentially what these protocols will do is that they will reduce their assumptions about the underlay, which is a great thing to do, yes.
Okay, so that's maybe why people are so scared of synchronous protocols. Yeah? We were discussing this in the first talk.
Absolutely, yeah. All right. So, one other question that I think is very interesting to answer. So we are talking a lot about the internet being vulnerable and it's really bad protocols that networking people, myself included, has developed and using, but it's not the only reason. In fact, these attacks are made arbitrarily easier because of the centralization of the infrastructure over which the protocols run. What do I mean by that? In Bitcoin in particular, that I have more studied, or I studied at the time, what's interesting is that the more important nodes are actually super centralized in the internet, from the internet routing viewpoint. So if I look at the number of hosting of the cumulative mining power as a function of the hosting network, what I observe is that mining power is very centralized. I know it's not news to you. I know there are miners, but there is a difference between centralization on mining entities and centralization on the internet perspective. Miners have something to gain from Bitcoin working properly. Internet service providers might have absolutely no reason to serve it. So this is a different dependency to keep in mind. Let's take an example. 10 hosting networks actually host almost 70% of the mining power. To understand how little 10 networks is, recall we have more than 70,000 networks in the internet. Were those hosting networks particularly selected? Absolutely no. Most of us, when we decide our internet service provider, put price as the most important thing. So just keep that in mind. We have a lot of centralization on the internet routing perspective, which makes all these attacks that we talked about so much easier. Not only is mining power centralized in very few hosting networks, but if we look at the cumulative connections, so what percentage of the connections among Bitcoin clients are intercepted by the same hosting networks, the picture is even worse. In fact, only 3 hosting networks among the 70,000 in the internet see 63% of full Bitcoin traffic. These allow them to do a lot of analysis on what's going on. It allows them to delay blocks, delay transactions based on what they want. This gives them an extreme amount of power that is not being modeled in the protocol when we talk about security properties. So that's something to keep in mind. So we have extreme AS level centralization. Of course, we have mining pool centralization. And another thing that is true in Bitcoin and is also true about in Ethereum is that, so not all prefixes are equal. Some are a little bit more protected because their owners have issued entries in RPKI that reduces a little bit how exposed they are. But what we found is that most of the mining pools are not hosted in this type of prefixes. All right, so I want to switch gears a little bit, both because the attacks that I talk about was in Bitcoin, but also they were older, and one could assume that, okay, the situation should be so much better now, she's just old. Unfortunately, our more recent work proved that similar vulnerabilities also exist in Ethereum and in the internet today. So I'll talk to you about two attacks, mostly focusing on one, which is similar and work in Ethereum. So in the paper, we have actually two attacks, StakeBleed and Knockblock. The two attacks differ in their target and how stealth they are. StakeBleed, its goal is to cause chaos, basically, to disrupt the network as much as possible. And Knockblock is trying to gain some more funds for the attacker. So let's see how they work. A very similar picture, we have the internet, which is, as we now know, a network of networks. And now, instead of our Bitcoin nodes, we have a peer-to-peer network of Ethereum nodes. And Ethereum, as of reasonably recently, started using proof of stake. That means that I have special nodes that also participate in the peer-to-peer network that are validators. What does that mean? They have actually lock state, and they have decided that they will run validator software to help maintain the blockchain. But again, validators communicate through the Ethereum's peer-to-peer network, which runs over the public internet. Now let's see what is the vulnerability in this case. Again, I have a blockchain, and every slot, which is 12 seconds, one of those validators would be responsible for creating the next block, so to extend the chain. So let's say the proposer is this node on the right, and they propose this new block. Then other validators in different committees will actually vote by saying, oh, this is who I believe is the head of the chain. So although what the actual nodes need to do in the peer-to-peer network slightly changes, fundamentally we do know that all the nodes need to know the state of the chain, what is the more recent block that has been propagated. More importantly, they are paid for being able to act upon it. So the particular proposer will be paid for proposing on time. The different validators that cast their votes for their head of the chain will also be paid for their ability to attest on the correct block. So now, an attacker that is able to prevent them from communicating with the rest of the peer-to-peer network is able to prevent them from actually getting these rewards. So if we try the same attack in which the attacker just tries to isolate the nodes on the gray zone, hence once the proposer, in this case node N, will issue a block, it will be only propagated within the gray zone, and hence the other validators will not be able to vote on this block, hence they will miss their rewards. Worse than that, maybe this block that the proposer created would never make it into the chain, hence they will also lose their rewards from that. What's even worse in Ethereum is that there is this inactivity leak. If nodes observe that a significant amount of the validators that are expected to participate in the network are currently not online for more than 25 minutes, what happens is that they assume they're away and they will start penalizing them more. So effectively, by keeping the attack a little bit longer, the cost for the isolated validators quadratically increases. In this diagram, we have the hijack time, so how long do I keep the isolated component independent from the rest of the network as a function of the total penalties these incur for the validators that I have isolated. And as you can see, once the inactivity leak has been enforced, the total penalties increase quadratically. What we found is that by hijacking 29 prefixes for only 2 hours, we can have damages of 300 ETH total. That's more than 50K, more than 60K dollars amount based on the, like I did this in the morning. So not only did proof of stake not solve the routing problem, but essentially even made it worse. So basically, how does this work? Again, I'm hijacking the validator prefixes, and because of this, I cause validators to miss their attestation and they'll block proposing. I create an inactivity leak after 4 epochs, and that basically create chaos. And to do this, I don't need any stake in the protocol. I don't need even an Ethereum node. I don't need to understand crypto. I just need a BGP router that can talk to the internet. I don't even need to be one of the 70,000 ASs. I just need to compromise one. Another important thing, I'll just mention 2 numbers here. So because of how centralized validators are in the internet infrastructure, me creating an inactivity leak is really cheap. I only need to hijack 29 prefixes. The amount of prefixes that I hijack affect how visible I am on the network. So an attacker will try to reduce this number as much as possible. And the reason I'm emphasizing this is that people will tell you that, okay, mining power cannot be that decentralized in the internet because, you know, you need power, you cannot just go distribute this everywhere. But this should not have been the case for proof of stake. There is not a fundamental reason why I should have all my proof of stake, all my validators at the same exact, or at very few internet locations, because that makes the attack easier for an attacker. Another important point is that we find that 59% of the validator's IP are not protected by RPKI. So not only am I going and putting all my validators in one place, I'm not making sure that their prefixes are somewhat protected. It is somewhat surprising, at least. Questions? Let me tell you a little bit about RPKI, because I skipped it before, but it's important to know. So we talked a lot about BGP hijacking and the effects of that. And of course, we have tried to solve this problem. The one solution that has seen some success is RPKI, if I find it. Okay, so in the default BGP hijack, the attacker says, I own this prefix, I propagate this, and regular routers have no way of checking whether they're lying or not. They just believe it. So there is some implicit trust. With RPKI, which is some infrastructure that we have come up with that connects the IP prefix with the entity, owners of prefixes can create entries, which we called ROAs, that connect the prefix with the entity. Hence, once a router receives an advertisement, they can go and check whether this AS that claims to own a prefix is actually the owner of the prefix. So while this could prevent some of the BGP hijacks that I talked to you today, there are 2 problems. One, deployment is quite low still, and so many of the prefixes do not even have such an entry, so it's impossible for routers to check anything. But more importantly, routers themselves have little incentive to actually check. Why? If you're an ISP, you're an internet service provider, and you do this check, and you drop an advertisement, there are two things that can happen. You were right, that was a malicious advertisement, so somebody else's benefit because they're not attacked. Okay, you don't gain anything, but you're good. The second case is that that was actually not a malicious advertisement whatsoever. Somebody issued their ROA wrong, or something else was happening, and you have actually just prevented your clients from visiting a particular location. So you are to blame. So RPKI could protect you against some BGP hijacks, but deployment is not great, and also it requires that people filter, which they have less incentives to do. This is why I'm emphasizing on the fact that it's weird that we have so many validators in prefixes for which there is no ROA. They haven't even tried to configure RPKI. And this is a people problem, yeah. It's not a technology problem per se. Okay. All right, my last attack for today, again, against the Ethereum. This is the case where I'm the attacker, I have a validator, and my goal is to just increase my rewards for the block that I will propose as a proposer. So what I will do is that I will go and hijack the previous proposer and benefit from doing this. I can always calculate who would be the next proposer 12 minutes in advance because of how proposers are being decided. There are ways of mapping IPs to validators. You can see more on the paper. There's also one paper from Professor Wattenhofer's group that does a different mapping, but like a different method for mapping, but you can consider that this is reasonably easy to do. So I go and hijack just one prefix for 12 seconds, enough for me to say, oh, that was a mistake. This happens all the time. Nobody would even notice. So we hijack this for just a few seconds, and that prevents the particular proposer for creating their block. They miss their own rewards. I get a little bit more rewards, and I even benefit from higher MEV. I have more opportunities to play with the order at which I have my transaction in my own block. So just a few numbers, I can turn a 91 reward into a 500 just by hijacking a prefix for 12 seconds. Yes?
So I don't know much about this, the depth of the BGP hijack, right? That once you do it, and once it's effective, and you manage to run the hijack, how visible it is, and what is, let's say, the real probability that you may end up like in jail or with, right?
Yes.
Because the beauty of these crypto scams is that usually you don't really end up in jail, right?
Yes.
So all of a sudden, $500 may not seem that much.
Yeah, I totally agree. So let's discuss this. What's the problem with BGP hijacks? Why can I get away with doing a BGP hijack? Because I can always claim it was an accident. And there's so many famous accidents, like, I don't know, like I'll just mention some, maybe you have heard them. For example, at some point, Meta misconfigured their routers that connected, there were two routers at the border of their data center. So that broke connection between the data centers, and they couldn't fix it because they couldn't even log in to the buildings. So what I'm trying to say is that it's really easy to misconfigure BGP, and the fact that you have incidents, Meta did it. Another incident is like Google actually managed to hijack about half of Japan for like half a day. They leaked a prefix which caused everyone trying to contact Japan to go to Google. Even Google could not sustain the load, so effectively they dropped the traffic. Half of Japan was offline for a few hours. It was so critical that the government of Japan required ISPs to report what they had done wrong and what will they do to avoid such an incident in the future. Did Google want to do this? No. So the problem is that you have so many incidents that prove that reconfiguring BGP in a wrong way is so easy to happen that I can always claim I didn't do it on purpose. Now, if you add to that I only hijacked it for 12 seconds, it was totally benign, I tried to fix it.
That's fair, but if I hijack it once for 12 seconds, completely agree. If I hijack it like every 12 seconds to bump up my reward, maybe it's a different story.
Correct. But what can I do is that I always hijack a different prefix because the proposer just before me would be in a different place. That's one. I don't need to hijack from the same place. That's the second issue. Okay, so this I kind of take it back because there was an AS that was like a serial hijacker. It was hijacking so often, it was like the top, it was making the top of all lists. It took years to persuade people to just not connect to it.
Okay, that's fine.
So I haven't seen any real consequences for anyone doing BGP hijacks.
Yeah.
Just a question about the slide. I'm confused by, on the one hand, 500%, on the other hand, 45%. Like why? So the attack would be, you already know you're going to be composing a given slot. You basically make sure the person right before you doesn't get to compose.
Yes.
So like very naively, you might think, okay, that's like 2 blocks worth of rewards. You might expect like 2x. So I'm trying to understand like where's that 5x coming from?
It's also I think it's also because I benefit from MEV opportunities and we calculated the average. So how much better can I do if I also take the MEV opportunities from before? And that could be affected by the fact that some blocks have really high MEV opportunities, so that could be as well.
This makes sense. So that's why if that had said like plus 400% there, I probably wouldn't have the question.
Yeah, it could be that my numbers are not great. I can also have to. But Kostas is there. Guy?
So when you perform the hijack, some slots remain empty, so the transaction pool still remains wide. This increases MEV opportunity, that's where the 44.5% comes up. And the 500 is just the block rewards. It's because at the stations do not get included in the hijack slots, so you include more at the stations. That's pretty much it.
So why would it not just double? Why is it 5x instead of just double?
You can hijack up to, you can hijack many more slots.
Oh, so I see. So not after possibly multiple empty slots.
Yes.
I was interpreting empty slot.
That was the previous rule.
Oh, yeah. Got it.
Anyway, I have a question. So, I guess large miners generally know that this is a danger that they face. So, can you maybe elaborate to what extent, or not at all, that they connect to multiple ISPs or multiple AS? They are aware of this issue, right?
Yes, totally, yes. So I can tell you for miners, what we had seen was that they were trying to be multi-homed. That means that they would propagate their blocks not from one location but from multiple. That totally help, as long as it's not easy for somebody to really see where you are exactly. So there are different ways that can reduce your exposure. Being multi-homed is one of them. I think a better way that I haven't seen people use is that you have multiple nodes within the same autonomous system. So in fact, by default, the peer-to-peer protocol will not prefer to connect with nodes on the same AS. For me, this is completely wrong because you cannot hijack within an AS. So the moment that I connect to multiple nodes within the same autonomous system, the attacker would need to find all of them and prevent them from learning anything from outside. Not only can they cannot hijack my connection to them, but they cannot see this connection because it's always within one internet service provider. So I think these connections are actually gold, and I haven't seen anyone talk about them. And in fact, the peer-to-peer protocol itself would discourage you from connecting to anyone near you, which proves how much we don't understand BGP hijacks or we don't take them into account. So that helps. Being multi-hopped helps. Relays could help. If you can find a way, A, to fund them, B, to not have people attack you because you introduce centralization. So all of these can totally help, yes. Even monitoring and identifying the problem, I think would definitely help. But that requires, you need measurements that last years and, the ability to talk to them and all these things. But there are ways to reduce your exposure, for sure. Yes?
Yeah, thank you for sharing the statistics of seeing the centralization of the mining and also miner or verifier. The statistics are showing that it seems to be the centralization is the key problem for the network level attacks between hijacking and others. And so you mentioned the multi-home kind of as a solution. And do you see the possibility without changing much in the network layer, be able to use any thing like the low latency and the customized identity network XOR system, not XOR itself, maybe customized lower cost core type of system. Would that be useful to hide? And so the existence or location of those manufacturers and also verifier cases such as for this that level attack wouldn't be able to happen easily.
Absolutely. Yes. Yes, totally. In fact, it's easier to talk about attacks. It's always easier to sell to people, academia, right? Solutions are harder. But actually, I even have a paper on this. So there is a way to decide the locations such that even though your validators or your Bitcoin or your miners are not in the same internet service provider, their connection cannot be hijacked. So I only talked about longer prefix hijacks, which are global, they propagate on the whole internet. But in fact, what I can do is that I can always advertise the longest possible, that I can always advertise as /24, and I can connect to nodes with which the connection is so economically good that an attacker will not be able to win over me. So the way that BGP decides how traffic is being routed is with, let's say, two criteria. One is the length. But if you make sure that you're in the maximum length, the attacker cannot propagate their advertisement better than you. So the only thing left is economic agreements. So if I'm always connected with an autonomous system, and the connection with this autonomous system is the most economically viable possible, there is no attacker that can create a better looking path from any routers. So I will be secure. Not because BGP was ever secure, but it was designed with economic criteria in mind. So that's a way to kind of do this. Now, what's the problem with this? The moment you start introducing this scheme, people start to get annoyed by the fact that you tell them where to put their miners on their validation. If you have an overlay network, a relay, that just, this is what we actually did. So we exploited this property and we suggested, look, if you put these 5 nodes on these particular AESs, or we have different solutions, some number of nodes in some particular AESs, they can actually protect all the Bitcoin clients. But then people would attack us in that, okay, so you're centralizing. So that said, you can totally, when you're selecting your peers, you can optimize for connections that are harder to be hijacked because they're more economically viable what then the attacker is most likely able to offer. So there are ways by co-designing your peer-to-peer with the internet infrastructure. But you have to also, make sure that people understand that this is a problem and everything. Yeah.
Thank you.
Yes.
There's some great examples of attacks here. But in these examples, say that pretty much any blockchain protocol can easily go into PGP hijacks, or
At the minimum, I think denial of service should be possible. Of course, as Alberto said. Alberto, yes. As Alberto said, if the less synchronous you are, the less effective those can be. But it's most about what are your assumptions about the underlying network and how much they do not hold in the internet. Also, you could have a solution where your blockchain runs completely in a data center, and that could be, do you consider this decentralized? That's not me deciding, that I cannot do BGP hijacks there.
That's hyper-liquid. It's respectable.
Yes. Yeah.
But for example, the Kakao example, right? That seems like you can replicate that on all sorts of DeFi applications, or
yes, yes. Anyone that offers a web interface, an API that users can interact with, is vulnerable to this type of attack. And what's more interesting is that, people assume oftentimes, oh, you cannot hijack Amazon's prefixes. That's not true. Even Amazon DNS servers, that's not true. We have examples. So nobody is really protected against these attacks. I cannot hear you very well.
Could you give an example of the BGP hijacks?
I can try it. I'm not that old.
Okay. So for the BGP hijacks, it seems like it's kind of trivial to do with very low cost. So why is the internet not flooded with malicious JS files and everything's just untrustworthy?
Oh, that's an interesting question. So there is all these attacks, the attack that I started with, right, the 2 million, no part of it was that innovative, but it's the sequence of things that the attacker is doing. They did the BGP hijack, they acquire a certificate, and then they offer the malicious JavaScript. So it's the chain of dependencies that I'm exploiting rather than a single thing that I'm doing.
That's fair, but it still sounds like the second step was easy for them to do as well, that obtain the certificate.
It's reasonably easy, and it does happen quite often. But, okay, so there are ways around it. For example, Let's Encrypt now requires, once you issue a certificate, Let's Encrypt requires that you verify you own the domain through multiple vantage points. So the BGP hijack will be less effective, or it will be easier for them to spot if you're doing this. So, or there are other certificate authorities that would not do this process. There will be a different one. There is the transparency log that shows who has issued a certificate. So there are some ways around it. There's two-factor authentication. We have some things that are being done. Now, BGP hijacks do happen often. What we don't see as frequently is sequences of well-executed attacks. Another thing to keep in mind is that it's not that typical for the amount to be that high, and hence you learn about it. Yeah.
Thank you.
I propose one more question.
I'm done with the talk, by the way. I can.
Remind you that only seeing between everybody here free alcohol.
I feel I did a really good job if I can prevent them from go to the alcohol. Yeah.
Who wants to do the honors of the final question? or to anyone's in the office.
So actually, it may actually be a stupid question, but the DNS, so the DNS providers, or actually your DNS register more than the provider, wouldn't such person be in the perfect situation to issue certificates, in the sense that you usually already have a sort of API key or out-of-bound authentication with that entity? They can make the binding between the DNS and your IP address by using that key. Is it a thing that exists, or that would make sense? Like Cloudflare itself, let's say, right? Or Portbun, rather than Let's Encrypt.
My short answer is no. It's already an infrastructure that has a lot of issues. I don't want them responsible for certificates as well. It's often that, so DNS by default is unencrypted, right? So that's already a problem. Should they be responsible for also issuing certificates? Okay, so I'm a networking person, so I think in terms of layers. I want to be able to resolve a domain name, and that should be independent of whether you're using authentication or not. I'm sure you can, there are things you can potentially gain. There is one more thing that we often talk about is deployability. So now you'll have to persuade everyone to follow your new protocol. Try to do this in IETF. Come back, we could talk or have a drink or two. So that's that. Yeah, I don't see. Here's what I don't see. I don't see why this would be better.
Okay.
Yeah, that's that. All right. Thank you so much for your question.